fourth and last lecture in our series for the 100 Years of General Relativity. Today's speaker is Tony Padilla. Tony did his undergraduate studies at Cambridge, followed by PhD at Durham. Then had postdoctoral positions at Oxford and Barcelona. He was then a Royal Society University Research Fellow here at Nottingham, where he's now associate professor in the particle theory group. Tony's going to talk to us about one of the most important questions in gravity nowadays, the puzzle of quantum gravity, whether we have a quantum theory of gravity. The talk's supposed to last about 40 minutes, followed by questions from the audience, and we encourage questions at all levels of technicality, but particularly, questions from non-experts. So I'll let Tony.
Okay, thank you. So I think I got the short straw, because I got the topic that was probably the hardest and definitely the most emotive of all the topics that have been discussed in this series. And well, I'm not exactly an expert on quantum gravity. In fact, I'm going to talk a little bit about one particular theory of quantum gravity, which is string theory. I'm not a string theorist, but I've been convinced by the arguments that reinforce that. Now, of course, it's wonderful to celebrate Einstein's achievements. I think any theoretical physicist would look at Einstein as a hero of theirs, along with Newton, Maxwell, all the greats. But Einstein's right up there, and somebody who had physical intuition totally unrivaled, I think. And he's quite an interesting character. I mean, I think people know that he was actually quite a lazy person in some respects. His first tutor, a guy called Minkowski, described him as a lazy dog. So not just lazy, but a lazy dog, so doubly insulting. He used to sleep for 12 hours a day. So I have two young children, and when they wake up in the night, my wife gives me a nudge. And I tell her, well, Einstein used to sleep for 12 hours a day, and she quickly reminds me that I'm not Einstein, which is a sort of sobering thought. Another little anecdote about Einstein. There's a colleague of ours, a guy called Stanley Dazer, who's older, shall we say, and he was a postdoc a long time ago in Princeton, and he was taken around Princeton by Oppenheimer, who you may know from the Manhattan Project. He was taken around Princeton by Oppenheimer, who was head of the group there. And Oppenheimer said to him, "Look, Stanley, you can work with whoever you want. You can do whatever you like, but there's one rule: don't talk to that crazy guy in the corner." I'm pointing at Ed there. I didn't mean to point at Ed. But of course, who was Oppenheimer pointing to? He was pointing to Einstein. So, well, crazy, but certainly maybe you have to be crazy to be a genius. So I'm going to talk today. I'm going to start by talking about two absolute pillars of 20th century physics. I'm going to take a step back 10 more years. We go back 100 years, I'm going to go back 10 years more. I want to go back to relativity itself, not general relativity, plain old special relativity. Because when you take this, special relativity, and you take the other great achievement of the 20th century, i.e. quantum mechanics, and you put those two together, then general relativity actually becomes inevitable. It's an inevitable theory of nature. Of course, Einstein didn't arrive at it that way, but we would have arrived at it that way, just by knowing special relativity and quantum mechanics, these two hugely important triumphs of 20th century physics. In fact, it's kind of incredible. Physicists don't just do whatever they want. There's not an anything goes attitude. Okay? In some respects, the greatest, we worry about experiments, what experiments tell us, but it's not the only thing that we worry about. We worry about quantum mechanics and we worry about special relativity, because these two things literally restrict so much what we can do. Consistency of what your ideas with the laws of special relativity and the laws of quantum mechanics really means there's not an awful lot you can do physics kind of becomes inevitable. And one of the things that's almost inevitable is general relativity. So whilst, of course, experiment's the great arbitrator, we're in a field which is very old, which is 400 years old, more even. Right? We've learned a lot. We've learned these things, only certain things make sense. And so we can, just as well as use experiment, we can use our minds to try to find the way forward. And it's not in a completely, just do whatever you want. There are rules that we have to abide by, and they're very restrictive rules. And that's part and parcel of being a theoretical physicist today. And of course, it's those ideas that lead you to general relativity. And it's also those ideas, I'm going to suggest, that will point towards string theory as the quantum theory of gravity. Okay, so let me start with a little overview of those theories that I've talked about. So let's go back 10 more years, 110 years. I want to talk about special relativity, truly remarkable. Okay, so let's talk about something else that was remarkable. And this is this event. This is Usain Bolt. This is Usain Bolt jogging his way to the world record in Beijing. Okay, powered by chicken nuggets, apparently. And of course, when you see that, and you see what he then went on to do in Munich, and all that, you think, wow, is there any limit to how fast this guy can go? You know, if you give him enough chicken nuggets, if you feed him enough, is there going to be any limit to how fast he can go? And then actually, he realised the answer to that is actually yes. He can't go faster than that. Not even Usain Bolt can go faster than that. What is that speed? It's the speed of light in a vacuum. Okay? But that's not what's really important about the speed of light. The fact that it's the maximum speed of nature, that's not what's really important about it. Okay? What's really important about the speed of light is that everybody agrees on what it is. Everybody agrees that the speed of light is the speed of light. It's that speed. What do I mean by that? Well, imagine this scenario, okay? You have a light source. There's light coming from light bulb, whatever, and you've got a tortoise and a hare, and they're both running towards the light. Okay, run towards the light. Something out of, I don't know, some dodgy science fiction program. But, so they're running towards the light, right? So the hare's going very fast, of course, the tortoise is going very slowly. And maybe they've got some way of calculating the speed at which the light's approaching them. And you think, of course, the light's approaching the hare much quicker, right? Because he's running towards the light. Whereas for the tortoise, it isn't. So the hare should measure a larger speed of approach, if you like. But that's not what happens. They measure the same speed. This is completely counterintuitive. You think that you just add speeds. You know, if I'm driving along the motorway at 70 miles an hour and you go past in the opposite direction at 70 miles an hour, then our relative speed is 70 plus 70, 140, right? Not quite. Okay? Because when you get to very large speeds that are very approaching the speed of light, that way of just simply adding speeds just doesn't work. And in fact, it can't respect. If it did just add speeds, you couldn't have this property that everybody measures light as traveling at the speed of light. You can't overtake light. Okay. And this is what's important. And Einstein realized this, again, from a pure thought experiment. It wasn't people talk about something called the Michelson-Morley experiment as being the inspiration behind Einstein's ideas. It wasn't really. The inspiration behind Einstein's ideas was just thinking about electromagnetism. And he thought that the laws of electromagnetism should be the same for everybody. And in those laws, there's the speed of light. So if one observer and another observer are moving relative to one another, and if they're seeing the same laws of electromagnetism, they must agree on the speed of light. This is what's crucial about it. But it's completely counterintuitive. You think about what's happening to you when you're driving in the car along the road, and the guy goes in the opposite direction. What you've got to do to accept this is to completely abandon the notion of absolute time. There isn't a big clock in the sky that we all agree on. Okay? There's just your clock, your own clock. And one of the remarkable facts that emerges from this is that time must actually slow down for moving observers. So if you're running along and I'm stood still, I see your clock as ticking a little bit more slowly than mine. So what does this mean for Usain Bolt? Well, let's think about it, okay? So he's running along, right? So he's a moving observer, so his clock is ticking a little bit more slowly. So it actually suggests that the time in the stadium clock will be a little bit more than the time on Usain Bolt's watch. So he ran it a bit faster, it seems. Okay, he actually clocked a shorter time. Does that mean he ran faster? And the answer is no, it doesn't mean he ran faster. He still ran roughly at 10 meters a second relative to the track. Okay? But also the track was moving at about 10 meters a second relative to him. And yet he clocked a shorter time. Ran at the same speed, just didn't change, but he clocked a shorter time. What happened? The only explanation is the track shrank. Amazing explanation, but the right one. The track actually shrank according to Usain Bolt's frame of reference. So he didn't even complete the race. Take away his gold medal, partly just because he's a Man United supporter. But anyway. It's about, the time is about, I think it's about 5 minutes of a nanosecond and a similar order of nanometers, the amount by which the track shrank. So this is the notion of length contraction and time dilation. The shrinking of Usain Bolt's, of the track, the slowing down of his clock. This is the incredible ideas that underpin relativity. Okay, so let's move on to something weird. And it is weird. I'm going to talk about quantum mechanics now. Now, anybody who thinks quantum mechanics isn't weird doesn't really know what quantum mechanics is. It's weird, right? So how weird is it? Well, let's think about it. If you want to try to get a picture of quantum mechanics, you have to think about the double slit experiment. It's the classic experiment which describes quantum mechanics. So let's think about it. Okay, so what I want you to imagine is you have a screen with two slits cut through it, right? And there's a screen at the back. This screen at the back is going to pick up, say, electrons. Okay, so we're going to fire electrons at these two slits, and at the back we're going to detect them. Now, let's just imagine for a second that these things are like particles. Very simplistically, I'm going to oversimplify this a little bit, but I just want to make the point. What would happen if you fired particles at this thing, you would imagine, naively? Well, the particle goes through either slit, and then you get sort of, well, really, you'd get sort of this kind of shape. That's what you'd expect, right? Just goes through either side. That's what you'd imagine if it behaved like a particle. Now think what would happen if you fired a wave at these slits. Now waves are a bit different, right? What happens with the wave? Well, it's going to come in, the entire wave front is going to pass through both slits at once, right? And then beyond the slits you get this interference, constructive or destructive interference. And then at the end you'd expect some sort of interference pattern. But the point is that the wave passes through both slits at once, right? So you get this very characteristic pattern that appears on the screen. Okay. So let's actually do, so those are the sort of two things you've got in your mind. Well, if it behaves like a wave, it's going to do that. If it behaves like a particle, well, it'll probably do something like in the first picture, surely. So you do the experiment, you start firing electrons. Well, what happens? Okay, so let's see. You fire them, you fire the electrons, and what's going to emerge? It's going to be those two lines, right? Surely. No. Weirdness happens. Weirdness comes in. And you start to see something that's more consistent with the wave. Okay? And this happens. This is just happens. What the hell is going on? This electron is behaving more like a wave. The electron is behaving as if it's passing through both slits at once. In effect, it is in two places at once. What this tells us is that really, all we can ever talk about are probabilities. The probability of the electrons at A or B, and in the end, you could describe something which is a wave, which describes both probabilities. Everything's weighted appropriately. You completely lose the deterministic notion of what quantum mechanics is, a determined notion of nature, and you develop this probabilistic notion of quantum mechanics. So let's just explore that a little bit more. Okay, so we're going to do Schrodinger's cat experiment, right? So what Schrodinger wanted to do was he wanted to put some radioactive material in a box. And let's just say it simplistically, there's a 50-50 chance that that this material is going to, you close the box, the 50-50 chance this material is going to leak and kill whoever's in the box, and 50-50 chance that it's not. So Schrodinger puts a cat in the box. I'm not going to do that because, I like cats. I don't like Jeremy Clarkson. so I'm going to put him in the box, okay? So it's a 50-50 chance that this stuff's going to kill Jezza, and or he could crock. He's either going to survive or he's going to die, right? You'd imagine. But it's so what happens? The box is shut. Okay. Well, here's both possibilities. Just as the electron passed through both slits at once, Clarkson is both alive and dead. This is a bit alarming, I know. It's both alive and dead at the same time. It's only when we open the box that he collapses into one or the other through a process which we call decoherence. So this is the mysterious world of quantum mechanics. So you put the mysterious world of quantum mechanics along with the incredible world of relativity, and what do you get? You get quantum field theory. Okay, this next bit of the talk is not for the light-hearted, but stay with me, because this underpins all of physics in the 20th century and beyond. This is a magnificent theory, quantum field theory. It's the most well-tested thing out there. I don't know if that's actually true, but it's very well-tested. Okay. Incredible precision with which we've tested quantum field theory. Okay, so what's the name of the game in quantum field theory? Okay, so you bring relativity and quantum mechanics together, you have quantum field theory. Okay, so what I want to imagine is, I'm going to fire, say, two electrons. Two electrons are going to scatter off one another. Okay, so here's my picture. The electrons come in, they interact, and they scatter away from one another. Okay, that's fine. How do I describe that in quantum field theory? Well, let me just trace out the path of the electrons. Okay, so I'm tracing out the path of the electrons, so you can see the electrons are going to, when they come in, they follow this path, right? And then they go out again. So I'm chalking out the path of the electrons. What does quantum field theory tell us describes this process? What do the two electrons do? Well, it tells us they exchange a virtual particle. This is why they scatter. This is why they repel one another. They exchange a virtual, it's actually a photon. Okay, something that you would associate with a particle of light. The two electrons exchange one of these guys. Exchange many of these guys. Now a virtual photon is not like something you can just grab. It's not like a real photon. You can't just sort of snatch it. It's virtual. You can't do that. Okay, it just interacts, it mediates the force between these two electrons. It's the picture that we have. All forces are like this. This is what they are. They're the exchange of these virtual particles. Now, what kind of particle you're exchanging basically tells you the nature of the force. If you're exchanging photons, this is electromagnetic force. If you're exchanging gravitons, that's the gravitational force. If you're exchanging gluons, that's the strong force. So on and so forth. Gauge bosons would be the weak force. Okay, so this is what forces are. They're the exchange of virtual particles. You can't just grab it, snatch it, and take it away. If we're interacting, the virtual particles will pass from one to the other. Okay, so this is the picture. This is quantum field theory. Now, let's take it a step further. Okay, so all of physics, this is how we think about forces now. So now let's think about gravity. Okay, so in gravity, I can have virtual gravitons which mediate the gravitational force, but I can also have real gravitons. They're gravitational waves. So we can have real gravitons, real ripples in space-time, if you like, that can themselves interact with one another through gravity. So I can scatter gravitons. Now, how do they interact? They interact by exchanging virtual gravitons. So I've got my two real gravitons coming in. They interact through exchange of virtual gravitons, and then they go out again. Okay, so this is a gravity scattering experiment. Now, just by thinking of this, and the rules of quantum field theory, and the nature of that interaction, okay, you get general relativity. You realize that gravity is mediated by a long-range massless particle that has something called spin 2. Don't worry about what that is. And it gives you general relativity. It's pretty much nailed on. Okay? You can try some other things. Right? The rules of quantum field theory don't allow you to do very much. Okay? And understanding what you can and can't do is important. If you want to start to try to solve some of the problems of cosmology, for example, you need to remember the almost inevitable, very bracketed, almost inevitable path that took you towards general relativity, just by thinking of these very simple scattering processes and quantum field theory. So, let's take a step further. What goes wrong? Well, let's go back to our electrons. Okay, so this is your two electrons coming in, scattering away. Imagine another one. Okay, now imagine I just sew these two pictures together. What have I created there? I've created like a loop within the middle of my diagram, in the middle of my process. So in a way, I can just think of this now as two outer electrons scattering. Now the thing that's mediating the interaction is this photon, but there's also this loop of electrons in there. Okay, I can build this up very naturally. Okay, to be consistent, it turns out I have to do this. So, in a way, I've sort of rebuilt what I think about the interaction, the force between them. There's this extra effect that can come in from, squeezing in these loops of other particles. And then you can ask the following question: what happens when I shrink that loop down? So I take it to zero size or infinitely high energies. So I shrink it down, I shrink it down, I shrink it down, and bang, what happens to my equations? Well, infinities pop out. So it's terrible, and you panic. So you think about, what a quantum field theory tells you, what a force is. It's the interaction, you exchange these particles, these virtual particles. Then you realize that you can start sewing together diagrams in a certain way, and you can create these loops within these processes. And then you say, what happens when I shrink the loops to zero? There's no reason why you can't do that. Out pops infinity. And this was a crisis of physics around the 1930s and so. So our theory, this brilliant theory of quantum field theory, is predicting these infinities. And then you realize, hang on, I can absorb these infinities in a redefinition of what I mean by the exchange of the particle. I can do it consistently. I just redefine what I mean by exchanging the particle. There are other infinities that pop out. Infinities that pop out when you start thinking about these sort of loops that appear when you start thinking about what it means to interact, what it means by an interaction. But again, you can reabsorb them back into a redefinition of where you started from. And in the end, you can consistently do this just by reabsorbing, redefining things, and you can keep everything, all these infinities, under control. This is called renormalization. Okay. So you can do this with the, when you start trying to quantize, say, electromagnetism, you get quantum electrodynamics, and it's completely renormalizable. You don't have any, but you can keep reabsorbing these infinities in a self-contained package, and everything's under control. It's complicated, but it's under control. And now you go back to gravity. Oh, hang on. Yeah, sorry, you try to play the same game with gravity. Same rules. Create the loops. shrink the loops. Infinities pop out. Oh, I'll just reabsorb that somewhere else. Oh no, I need to find and create something else to reabsorb it into, but that's okay, I'll just carry on. And eventually what you find is you keep having to introduce more and more and more and more things to absorb all the infinities that you just keep generating. You're generating infinities everywhere. You introduce something else to absorb that infinity, then you go, oh no, let's create another infinity. Oh no, there's infinities everywhere. They just run away from you, they take over. There's no way you can ever keep them under control. They overwhelm you. Whenever you think you've absorbed one, another one appears that you need to create something else to absorb that, and it just gets out of control. In a way that doesn't happen for the other forces. Happens for gravity. Gravity is not, we say it's not renormalizable in the way that the other forces are. So why is gravity so much worse behaved? Okay. Well, this is back to the interacting electrons, right? What this process tells you, there's a number you can assign to this particular process called the amplitude. What the amplitude tells you, it tells you the probability that the electrons are going to scatter through a certain angle. Okay? Now, that probability is not supposed to exceed 1, are they? You can't have a probability that's greater than 1. What does that mean? Right? So you look at this process and you say, what's the probability? You do your relevant calculation. You say, I can extract a probability that tells me the probability the electrons are going to scatter through some angle. Okay? It turns out this is always nice and small. Okay? It stays small. It's good. It's well behaved. It's small. Good. That makes probabilities not bigger than 1. That's good. That's consistent. And that's part of the reason why you can then build it into a much more sensible theory. When you do it for these graviton scattering, when you start scattering these particles of gravity, and you say, right, what's the probability they're going to scatter through some angle? Fine, you calculate it. And then you realize that number just gets bigger and bigger and bigger as you increase energy. As you increase the energy of the system, that number just goes up and up and up and up. Eventually it gets bigger than 1. And you're like, oh, what do I do now? What you normally do, you have to do something, okay? The question is what? And that's the problem with quantum gravity, right? But this is at the core of why, things just aren't as well behaved for gravity as they are for the other forces. The fact that eventually, the probabilities associated with this process just get bigger and bigger and bigger in a way they don't for the others. They don't stay small. Okay, so how do you fix it? Well, let's take a step back. Okay, so you have these scattering gravitons. Okay, and you can calculate a formula that describes the probabilities that's valid at low energies. Great. And this is what you do. You say, okay, I'm going to guess. This formula I have doesn't work at high energies. It gives me probabilities that are bigger than 1. I'm going to guess an answer, some extension of this formula, that gives me the same answer at low energies, but at high energies is well behaved, is better behaved. So I'm changing the formula, just the formula, at high energies. So at low energies it gives me the same answer that I can calculate and agrees with what I see. And at high energies it doesn't blow up, it stays below 1. I don't get any manifestly weird behavior. And I apply some other rules to the game that I know from quantum mechanics. I can't have I can't be introducing any unstable particles. There's no weird interpretations of this formula that you would associate with it. So you come up with this formula, right? At low energies it agrees with what you know, and at high energies is well behaved. Say, oh, this could be the formula that describes quantum gravity, right? And we have such a formula. And then when we try to reinterpret what that formula is, we realize that it tells us something about this interaction. That it's not really scattering of gravitons, it's actually scattering of strings. Okay? So this is the idea. It wasn't like we just said, oh, imagine particles are built out of strings. Yeah, that'd be it. It didn't work like that. We tried to extrapolate the formula that described the scattering of these gravitons at low energies. We knew it went wrong at high energy, so we just tried to correct the formula in a way that was consistent. And it turned out that it corresponded to a theory of interacting strings. Now, in the 45 years or so since that formula came out, nobody's been able to come up with another formula that can consistently extend that original low energy formula that we had. Okay, so it's possible it's unique, maybe it's not, maybe there is another formula, but no one's come up with one. So this strongly suggests that the theory of nature is built up from these strings. And it turns out the strings can also describe all the other stuff as well. It's not just a theory of gravity, it's a theory of everything. In fact, it doesn't really make sense to be asking, what is the theory of quantum gravity, and only think about gravity. You've got to worry about what matter is. You know, when you go to high enough energies, it's not just the gravity that's going to be behaving quantum mechanically, everything else is as well. Don't ignore it. String theory doesn't. It has everything in one package. Everything is there. A lot of stuff's there. Maybe too much stuff's there. But everything is there. So some people say it's the only show in town. String theory. Now actually people are trying to prove that it's the only show in town as well. There's some ideas where you start looking for consistent low energy theories, and you want to argue that actually the only way to extend that, the only way to extend it is via strings. Okay, now that's not proven, but people are working on it. Now notice, if that's true, if you can show that the only way you can have low energy gravity coupled to other forces, and the only way you can extend that into the UV, into the, into high energies, is through strings, then you don't need experiments to tell you that string theory is right. You already got the experiments, it's the low energy experiments. Because the only consistent structure that takes you upwards is string theory. Okay, what does string theory tell you? Well, this is the idea of a string theorist joke. I'm not a string theorist, so I can take the mickey out of those rubbish jokes. So you've got your string theorist, and he's going, oh, all the building blocks of nature are little tiny vibrating strings. Way. His mate goes, well, what does that imply? Oh, I don't know. Well, it's probably because he hasn't been able to get a postdoc. Right? No, what does it imply? Well, it implies that you have a quantum theory of not just gravity, but of other forces as well in some combined structure. Brilliant. It also implies something else. And he answers this, but he says it a bit quietly. So he goes, well, okay, what would that imply? And he goes, we live in 10 dimensions. What? I live in 10 dimensions. Did you say 10 dimensions? Are you serious? Have you actually gone crazy? But if it's inevitable, if it's the only theory it can be, then you have to swallow this, right? And it's a kind of a testament to how difficult this problem is that we swallow this. Okay. In fact, string theory is kind of unique in that it's the only theory that I'm aware of that actually predicts the dimensionality of space-time. Get a funny answer out. It's a bit annoying. It's only consistent in this number of dimensions. It's not consistent in any other number of dimensions. So what does it even mean to have 10 dimensions? What is that? Well, you have to understand what a dimension is. A dimension is just a direction that you can go in. So if you like, I talk about 3 dimensions of space because I can move up and down, left and right, or forward and backwards. That's 3 kind of different directions that I can go in. I can also move in time, so that's the 4th dimension. And if there are extra dimensions, then there's just extra dimensions I can move in. So if you're having trouble picturing that, then let's just imagine what would happen if you lost a dimension. Let's picture it. So this lady's going to lose a dimension. Nice 3-dimensional person. And look what happens. So she's turned into 2D lady, which is terrible. But you can see what's happened. She's lost her direction, right? She's become completely flat. So if you want to know what it's like to gain some dimensions, just reverse that process. Get back in the lift and, okay, whatever. So then you have to address this question. You can't ignore this question, right? If you live saying, oh God, there's 10 dimensions. So why do we not see them? Okay, well, you have to now start to answer this question. So there's a standard answer. It just has a little bit of magic. Okay, why are there ants on this wand here? I used to have a magic wand that I demonstrated this with. My daughter snapped it. So. Anyway, okay. So what does the wand signify here? Okay, so I want you to imagine a magic wand, and I want to imagine 2 ants crawling along the wand. Okay, on the one hand you've got little weedy, pathetic English ant underneath, right? Okay, he's a little weedy, rubbishy ant. And then the other one is big, scary South American ant, right? He's from the Amazon, right? He's got big. Okay. Now these 2 ants are going to do an experiment. They're going to calculate what is the dimensionality of the surface of this wand. Okay. So South American guy goes first. Okay. Say, talk to him in Spanish, probably, or Portuguese, but you say, what's the dimensionality of the wand? And he starts walking along the wand, right? I can walk along this direction, so I can detect at least one dimension. Okay, but he's too big to notice that he can also walk around that way. Okay, so he only notices that dimension there, so he says it's one-dimensional. English guy comes along, a bit freaked out because the other one's massive. And he's like, okay, you do the experiment now. And he's like, yeah, I can see that I can walk along that dimension there, but I can also walk around this way. So actually, I think there's 2 dimensions. And the reason they disagree is all about scale. The little ant is able to probe physics on a much shorter scale than the big ant. So in a way, what's happening is, it could be that these extra dimensions, these 6 extra dimensions, they are there. But they're just so much, they're so small. They're small, compact dimensions, like that dimension of the wand. Okay? And we're just not able to probe the physics on that kind of scale to see them. That's the standard boring possibility. The more exciting one is this. Ants on toilets. Well, not toilets, okay? What is this? This is the idea that we live on what's called a brane. So I want you to imagine this room, right? This room is the 10-dimensional room. And this wall has got a lot of ants on it. Now these ants are not allowed to get off the wall. Okay, their entire existence is bound to that wall. That doesn't mean this room doesn't exist, but their entire existence just kind of knows about that wall. There may be other walls. But their world is effectively completely 2-dimensional, right? Because everything they do is bound to that wall, and yet there's this 3-dimensional room. That could be the picture of our universe, that we live on this 4-dimensional wall in some 10-dimensional room. Okay? And the only way of interacting with the 10 dimensions is through gravity. But you can play around with the structure of the extra dimensions and the sizes of the extra dimensions. They can still be quite big. And you wouldn't even know that the room was there because you're like the ant stuck to the wall, to the toilet. Okay, it's this is the idea of brane worlds. And the nice thing is that string theory actually predicts that these objects exist, these walls. Okay, that they actually exist. So string theory, which created the problem in the first place by demanding 10 dimensions, is also offering a solution. Well, maybe you live on one of these brane universes. And you can start to wonder about what that means. Could these branes collide? There's various possibilities. They could be very weird, these other branes. There could be other branes, they could be very weird, different numbers of dimensions to them. Things could be very different on those other branes. You could think of them as like parallel worlds. Now, is this all just there, whatever? Yeah, you're just talking now. the experimentalists come along and say, well, can you ever find evidence for this? Well, these are testable theories. In principle, if we find any violation of those laws of special relativity, we know that string theory can't make sense. So it's testable. We're also looking for evidence of these ideas in this bad boy, the biggest experiment in history. You need a big machine to do play some of these games. This is the Large Hadron Collider at CERN. So what do they do at CERN? Well, they fire protons together. So what I want you to imagine is, you have a proton. Okay, so you have a bundle of energy. This is a little grubby rag, is a bundle of energy. Okay, and you pack it into a proton. And then you fire the protons together. Okay, and smack them together. This is what you do at the LHC. Now you're watching, and imagine this happened. Okay, you're like, where's that energy gone? Don't say in my pocket. Okay, where's the energy gone? Right, so you look for a process where there's missing energy. It's gone missing. And one possibility is it's gone into the extra dimension. You've managed to excite things at sufficiently high energies that energy's managed to escape into the extra dimension. That's something that we're looking for at the LHC, evidence of extra dimensions through missing energy. It's not the only thing that could happen. Okay? It's not the only thing. There's something else, much more remarkable. But it's symbolized by this. So I guess by now most of you may have heard, you're the kind of person that comes to this talk. I'm sure you read in the news a few years back, people fretting because they're going to create a black hole at the LHC. No, run for the hills. All right. Well, they might. Okay, it's precisely these scenarios where you have, where we live like the ants on one of these walls, where if those scenarios are true, you would potentially create black holes at the LHC. The reason that happens is because in those scenarios, it turns out that gravity is a much stronger force than you realized. It just looks weak to you because you're residing on one of these walls, but in reality, it's a much stronger force. And if it's a much stronger force, it's much easier to produce black holes. It's so easy enough that we could start creating them by smacking protons together at the LHC. So you could create these black holes. It's going to swallow up the Earth. No, it isn't. You don't have to panic. Okay? No, the end, yeah. No, don't, calm down. Not ending the world. The kind of black holes that will be produced at the LHC will be very small, order the size of the collisions. And so, very small black holes are very hot black holes. Black holes aren't really black, they give off something called Hawking radiation. When you apply the laws of quantum mechanics to the event horizon, the sort of point of no return of a black hole, then you find that they can give off radiation. And the smaller a black hole is, the hotter it is, the more quickly it will evaporate. Okay? And it will do so in a very distinctive way, actually. It will be completely democratic in the kinds of particles that it will emit, and it will emit equally in all directions. So what will happen is it'll light the detector up completely equally in all directions and completely democratically in the kinds of particles it's producing. And it's kind of unique in that process. So if we see that at the LHC, we see evidence of a black hole forming, then it's a strong pointer to these ideas of branes and so on, and extra dimensions and string theory. So that really is the end of the talk, not of the world, thankfully. And I'll stop there.
Thanks very much, Tony. So, have some time for questions. Anybody? Please.
I was told that we cannot completely test the string theory.
It's not true.
Can we test string theory at all?
Yes. You can test for, I gave you a very clear example, which is you can test for something called Lorentz invariance, which is basically the laws of special relativity. String theory relies on that. So if you find any violation of that, string theory is gone. Okay, so that's one example, for example, where you were looking for something that is an important property of string theory. String theory doesn't make sense without it, and so you look for it. You look for violations of it, and so in that sense you're testing it. Another thing that supersymmetry requires, string theory requires is supersymmetry. It's a special symmetry of nature called supersymmetry. String theory requires that to be consistent. Now the scale at which supersymmetry we've never detected supersymmetry yet. If we detect it, it's a feather in the cap for string theory. Okay, the fact that we haven't detected it yet is it's not killing string theory, because it could just be that we haven't probed high enough energies yet. But yeah, I'd say it's wrong to say it can't be tested. It can. There are aspects of it which can be tested. Essentially, properties of its low energy theory, without which it couldn't be a consistent theory.
Other questions? So let me ask one.
Yep. You allowed?
Does it have to be insinuated that it doesn't have to be tested? So that's a dangerous statement to make.
Actually, I would argue that in some respects, does it have to be tested? You could test the low energy things from which it follows, if it follows uniquely from very important low energy assumptions, i.e. simple rules of relativity of quantum mechanics.
If I always entails assumptions, right?
Sure, absolutely. So you test those assumptions.
If I'm willing to give, but no experiment will test these assumptions to infinite accuracy.
Well, no experiment will test anything to any to infinite accuracy.
Exactly.
It all becomes a...
So I cannot prove that any theory follows uniquely.
No, I can prove it. From certain assumptions, I absolutely can, right? So, and that's what people are trying to do. So you kind of start off with certain underlying assumptions. Those assumptions are well motivated because they agree with experiment very strongly at low energies, and then you could try to argue, and this hasn't been done fully yet in the case of string theory, but you can try to push those to higher energies and show that the unique path is, mathematically now you can try to show the unique path is string theory. So people are working on that, and it's an open question.
Fact, right? So my question lies on a different part, which is I make assumption A, B, C.
So you test those assumptions that led you uniquely to
finite accuracy.
Yeah.
Then I extrapolate the theory as a unique theory based on these assumptions that I tested.
You want to argue that the error grows.
I don't know how the error grows. What I'm saying is that if one of these assumptions is wrong by a little bit, the whole mathematical construction, which is exact, falls apart.
Well, if we abandon relativity and quantum mechanics, one or the other, then we're going to have to completely rethink physics. Now, maybe you could do it consistently, but it's much easier, as you know, to quantize gravity if you abandon Lorentz invariance.
Yeah.
So, okay, maybe that's one possibility, but we have to detect it. And actually, then you have to wonder why we haven't detected it. Alrighty, okay.
Speaking as an experimentalist, I mean, it's quite hard to find really good experimental PhD students and postdocs. They all seem to pile into this field or just the further reaches of cosmology. Is it worth it?
Is it worth it?
Yeah, I mean, at the moment, it's been a fantastic industry for generating jobs, and they're all Voigt and these Smollet's criticism of string theory. But is it all worth it? I mean, these guys, you can only get a faculty position in some of the theory departments. MIT, Caltech, if you do string theory. But when are you going to produce something interesting and new?
So hang on. Firstly, surely you're in the game to try to understand the truth of nature, right? Okay. Now, I think it's fair to say that people say, it's a closed shop. No, but this isn't right, okay? Because the bottom line is that those people that have excelled and become great string theorists have got into string theory from many different paths. And they've excelled, they've made contributions in other areas of physics. Let's take someone like Juan Maldacena, a great string theorist. He's also made huge contributions in cosmology. So how is he able to, a guy called Juan Maldacena, okay? Huge influence in cosmology as well, right? And so it's no coincidence that these people are somehow able to just do it everywhere. Whatever they take their hand to, they excel. Okay, and yet they choose string theory as the correct path. Now, are they right? Well, they tend to be right more often than they're wrong. Now, of course, we should always question their ideas, and that's the name of the game of science. Right? But I don't think it's fair to say you can't get a job unless you do string theory. I'm not a string theorist, I have a job.
Large numbers of talented people.
Who?
String theory, I mean, it's been a big industry for 20 years. A lot of people have gone in. And what are the tangible results?
What are the tangible results? Well, of course, there's been...
Other than simulation maths and possibly some applications of cosmology, which again may not be very testable.
Right, but, okay, so again, I think at the end of the day, if we can develop a theory, if we could build it, if the program to prove the uniqueness of string theory bears fruition, then what are you criticizing people for identifying the true theory of nature? Now, and the rules, and this is what I try to emphasize, it's not just experiment that can drive physics now. Also, the ideas of consistency of ideas could drive physics as well. And so we should embrace, we're an old enough field to be able to do that. We're not like biologists, we've only been around 5 minutes. If there's any biologists not around. But we've really developed a clear, consistent, fundamental picture of the way things are going on. And we should use that. As well as, of course, experiment is always the ultimate arbitrator. But realistically, are we ever going to be in a position where, certainly not in our lifetime, where we're directly asking questions about the scales at which you really would start to probe quantum gravity effects directly? Is that ever going to happen? It's certainly not going to happen in my lifetime. Now, could it happen in the future? Well, I mean, the first person to realize that the scale appeared in nature was Planck. Right, when he did some you love dimensional analysis, Lawrence, and he played around and he spotted out popped the Planck length, 10 to the minus 35 meters. Right, this is a ridiculously small length, and at the time they'd barely probed anything like that. We've still barely probed anything like that, but we still leapt orders of magnitude down the line.
And it's let that one go. Johnson Stoney, who was an Irish physicist,
okay, go on.
predicted a length scale which was 137 times shorter than Planck's length, just by using the electronic charge, gravity, and
okay, all right, but
non-quantum.
So it's smaller. It's smaller than the. Okay, I don't know about this.
By structure constant,
Okay, well.
So it wasn't Planck. It was actually a British.
All right, but we're going to arrive at the Planck length first, right? And there be dragons there somewhere to be discovered.
The mark of good theory is that it can make predictions, not predictions as suit for string theory.
No, I would say the mark of a good theory is that it's right. Now, okay? Now, what predictions string theory makes? Well, it predicts that nature should be Lorentz invariant, should satisfy the laws of special relativity. Actually, in a way, it grew out of that. So there you go. It predicts supersymmetry.
You predict it assumption.
Yes.
Somehow.
But it's only consistent. It's only consistent with that assumption. It's only consistent with supersymmetry. So they're predictions of it. Doesn't make sense without those. So they're predictions of it. If string theory is right, nature is supersymmetric, at least at some scale, and it's Lorentz invariant. Those are predictions. Yes, they were the assumptions, but you built the theory, and it has to be consistent with those assumptions. So they're predictions of it. So, but I shouldn't just rely. You call it a theory. It describes all of. Another thing that string theory predicts. It means it predicts. Since we're in the prediction game, it predicts a low energy classical theory that involves gravity. That's an important prediction, and not all theories of quantum gravity do that. In fact, string theory is the only one. Well, they're Lorentz invariant. let me be diplomatic about that and say, I think there's some way to go to I think we have to, if the uniqueness of string theory gets proven within the next 20 years or so, then I'd be happy to say it's string theory. But that's not the case now, so no, it's not solved.
So like my understanding of string theory comes completely from your presentation. I don't know much background either. But I was just asking, like, in your presentation you said that string theory was an interpretation of formulae that was consistent at high energies from something that was experimentally tested and worked at low energies.
Yeah, quantum field theory.
Yeah, so essentially when you say that string theory is testable at low energies, surely that low energies was initially used to build string theory.
Yes,
So,
that's fine.
what I'm questioning is like the results of those experimentations didn't actually come from having string theory as
No, those experiments were, you know, they were seeking a truth about nature. Okay, and from that truth about nature, you discover string theory pops out. So let's say we develop the uniqueness of string theory. Let's say that, I mean, that's not proven yet, but let's say eventually it does get proven. Then within those assumptions. Now, you continue to do those low energy experiments, and you continue to probe them, you know, perhaps to greater and greater and greater accuracy. And then now you are testing string theory. Because if you find that those laws break down, if you find like a violation of Lorentz invariance, then you are disproving string theory. Because you started with something you believe to be true, to good accuracy, but you assume it's completely true. You build string theory from that. And then you keep doing those low energy experiments, and you find, actually, that wasn't quite right. String theory dies with it. So you are testing. Yep. Oh, you do it.
Go ahead.
So you were talking about Lorentz invariance, how string theory predicts that. So my question is, does string theory predict that Lorentz invariance cannot be spontaneously broken?
No, of course not. No.
So then if we do...
Well, it's broken.
So if we detect Lorentz breaking,
A hard break? No, I'm not talking about. I mean, of course, it's spontaneously broken. I mean, I don't really know. It clearly is around me. It's clearly broken. But of course, when you spontaneously break a symmetry, it's still there non-linearly in the low energy effective theory anyway. So, of course not. No.
If we find a new point in which you would say, for example, we find a way to prove that the symmetry can't occur, if the work into it still be worthwhile?
If we find the string theory was wrong. Well, I mean, there's been a lot of beautiful maths developed from string theory. Another thing that developed from string theory is this notion of holography. Well, I mean, in black hole studies, but also it can have a concrete realization of string theory. This is the notion that you can describe gravity in, say, whatever number of dimensions, let's say 5 dimensions, 5-dimensional gravity. You can describe it using a quantum field theory in 1 dimension less. There's some beautiful maths and beautiful ideas that have come out of it. If it turns out to be wrong, well, we still have those. Now, yeah.
More questions?
It's so it doesn't really matter. You can have, I mean, space-time effectively emerges out of string theory. Actually, the curvature, the thing that you know, what you call the metric of space-time emerges as just a coupling constant of string theory. So yeah, it's you can formulate it within like a sort of, yeah, so it both. It incorporates flat space and curved space. It can easily incorporate both.
More questions? Let me push you one more time in the same direction. So again, in your talk, you sort of motivated string theory saying I have special relativity, I have quantum mechanics, I build consistently quantum theory. It explains to us how particles interact. I push that boundary further and further to higher and higher energies, and I get as a unique outcome string theory, right? So essentially you're putting in the assumptions of special relativity and quantum mechanics, right? And again, these are, as I said before, are assumptions which we test in our experiments with finite accuracy. Actually, when you do this process and you get string theory,
you're assuming it's exact, yes. So you're assuming those rules are...
Yeah, but the point is the underlying, when you try to do it consistently, it actually doesn't work, as you said, right? And you have to assume that there are like 10 dimensions, for instance.
Okay.
Right? Which is also an assumption of special relativity and conventional quantum mechanics, right? We live in 4 dimensions. And we don't, you provided
no, I don't think
an explanation of why we don't see these dimensions, right? But again, this explanation pushes them to assume that they're small enough, so it pushes their detectability more and more and more in order to explain why we haven't detected them yet, right? So I could do that to the other assumptions that you just put in. You say, I haven't detected Lorentz symmetry violations, I haven't detected, whatever assumptions come into my other theories, I just violate them. Just to an extent that it would not have been detectable today, in the same way that I haven't detected the higher dimensions that you want.
Yeah, I mean, obviously it's true that you're not just assuming 4-dimensional Lorentz invariant, you're assuming full d-dimensional one, and then you extract what the d is. Yes, that's true.
So all I'm saying is, if I give up, if I relax my assumptions...
If you relax any of the assumptions, then string theory...
all of my assumptions exact, even string theory doesn't fit the bill, right?
Well, what's the...
Like some other assumptions, like, as I said, higher dimensions.
No, it depends what your assumption is. I mean, yes, if your assumption is Lorentz invariance and quantum mechanics, full stop, then you're led very naturally, not yet proven uniquely, but led very naturally towards string theory. If you say, my assumption is 4 dimensions plus is quantum mechanics relativity plus 4 dimensions, then yes, okay, then you're led to nothing. So something that there can't be a theory like that. Well, that's not technically true, but for the purpose of this context of this conversation, let's say it is.
More questions? Well, I'm not forced to be more unbiased. Okay, so if we don't have any questions, I think we can just thank Tony again for a wonderful talk. Thank you all of you for joining us for a fourth time. Sorry, I had to play the other day.